Great, welcome to everybody to this webinar for May in 2017 with the Soils Network of Knowledge, as we call ourselves. It's sometimes call it SNOC. It's brought to you by the New South Wales DPI Soils Unit. So now it's a great pleasure to introduce Dr. Ehsan May, who's presenting today's webinar called Improving Grain Yields on Hostile Soils. Ehsan is a research scientist with over 10 years of research and consulting experience in soil fertility and crop nutrition, subsoil constraints, environmental nanotechnology, and soil-plant interactions. He's responsible for the soil science labs at Wagga Wagga Agricultural Institute, where work in soil chemistry and physics is undertaken. Dr. Tavakoli has been involved in and led a number of projects co-funded by GRDC, ARC, DAF and the Australian Synchrotron. He currently leads the New South Wales component of various national GRDC programs on improving wheat yields in sodic and dispersive soils, amelioration of sodic and acidic soils, and understanding crop responses to modern fertilisation techniques with a focus on improving subsoil fertility. Over to you, Ehsan.
Thanks, Luke. Good morning, everyone. It's my pleasure to present some of our research in Wagga Wagga Ag Institute that's been undertaken over the last couple of years to you this morning, and thanks for being on the webinar. So before I start the webinar, I'd like to acknowledge all the people who work with me in the soils group in DPI Wagga Wagga Institute, Graham Poyle and Albert Oates, Bin and Vince, plus Han and Yan. So behind all the work that I'm going to present today are a bunch of passionate people who always do the hard job. So what I'd like to start with is just to represent the gap that is available at the moment between the farm yield gap and also the potential yield. So over the last 2 decades, there has been a steady progress in increasing farm yield, and this has been the result of variety improvement, better fertilizer decision, better chemicals to treat the weeds and everything. But however, we still have a gap from the farm yield, what we can achieve, and the potential yield, which is water limited. So the potential yield is the yield that can be expected with the best adopted variety, with the best management of agronomic and also in the inputs, in the absence of manageable stress. Okay, so that could be a biotic or abiotic stress, like diseases and subsoil constraints. And what you see on the map of Australia on the right-hand side is actually that gap that exists in the grain belt of eastern, southern, and western part of Australia, which is anything from 1 to 2.4 tons per hectare. And that gap is due to many reasons, one of them being subsoil constraints or soil constraints, if you'd like to put it that way. So effective use of water stored in deep soil water is one of the key to close that gap. And some calculation shows that additional 10.5 mils of water during a spring, if the plant have access to that, is equal to 0.6 tons per hectare of extra grain yield per hectare. So that sets up why it's important to manage the subsoil constraints if it is manageable. There is a gap from when I change the slide, so I will wait for the slides to be presentable, then I'll start talking on the newest slide. So the next question is that why do we care about subsoil constraints? And basically, one of the main reasons that the cropping areas are increasing and the chance of hitting into one of those areas with subsoil or soil constraints is high. And root growth in alkaline, acidic, or sodic soils, which are various type of constraints, is often poor because of that limited access to the subsoil moisture during the spring. And most of these soils suffer from one or more than one either elemental toxicity or nutrient deficiencies, which declining the soil fertility. So improving yield and farm profitability in these conditions is quite important. Again, this map of Australia shows the severity of the spreading of the subsoil constraints. In this case, is dryland salinity and sodic soils across Australia. This is not just a farming area, but in all the soils across Australia. And so what it shows is that it's a quite an important issue to be tackled. The type of subsoil constraints can be basically divided into two categories. Chemical constraints, the most important one for Australian systems are soil acidity or sodic soils, and also high pH soils or issues with salinity. And physical constraints can be divided into compactions and waterlogging. In most of the cases, these two are interrelated. For example, if you have a sodic soil, that soil is also prone to be waterlogged because of the poor structural condition of that sodic soil that make it difficult for water to penetrate. However, the story is much more complex than what we can see in those 4 or 6 categories. In real life, in a farm situation, if you consider the pH, the sodicity, and the salinity together, it comes up with a very complex situation. For example, I focus on the box which is on the bottom right-hand side. If you have a sodic soil and the soil is a neutral, it has a neutral acidic pH. In addition to that sodicity problem, you have also issues with waterlogging and elemental toxicity like aluminium toxicity. So you have 2 issues happening at the same time. If it is sodic soil, has a pH from 6 to 8, often you expect a soil structural problem, and you get seasonal waterlogging and potential sodium toxicity. And if the soil has an alkaline pH, you are expecting to have, again, a structural problem because of sodicity, but also problem with carbonate toxicity or problem with aluminium deficiency or aluminium toxicity or iron deficiency. Okay, so what it shows here, it's a very complex issue when you want to put it in picture, because there are a few things happening at the same time and makes it very difficult to be managed. And just some back of envelope calculation shows that if we have subsoil acidity in our farm, it's about $141 per hectare per year, which is equal to about 1.6 billion per year of loss in productivity in Australian systems. And subsoil sodicity, based on that calculation, is about 0.6 billion per year. So from farm economy perspective, it's a very important loss of production. So how we manage this issue. So subsoil constraint, we often treat that issue as a scientific problem, but we really need a farm-based solution to tackle this issue. There are 2 approaches. One is to have a better variety that is adapted to that hostile soil condition. So we can have a better variety that have a trait which is tolerant to that condition, or we can have a management practice for the soil to alleviate the problem of subsoil constraint. And with the variety, over the last couple of decades, there are a lot of good research being done on that aluminium toxicity or salinity. However, if you remember the slide I showed you in the before, it's a complex issue. If we just breed a variety for one single trait, it's often problematic, because if we have 2 or 3 different stresses happening at the same time, we need a variety which has tolerance to multiple stresses. And in the long term, the best strategy is to have a dual approach that combines management with better varieties. And that is just the platform of what I want to go through. So I will talk about two of our recent projects. Just a snapshot of what we are doing in Wagga with improving wheat yield in terms of variety improvement, and also in acidic soil, and also management of an acidic soil. That is a project that is also co-funded through GRDC. So in a typical sodic and dispersive soil, one of the issues that we have is the soil clay disperse, and when we have dispersion because of high sodium concentration, the structure of the soil is in such a way that doesn't allow the water to go to penetrate into the subsoil, and you have waterlogging. In some cases, if you have a sensitive variety to high sodium concentration, that waterlogging and high sodium concentration also trigger the pathway for the sodium to go into the plant and make some sodium toxicity, which is also toxic, which is declining the yield. So we have a chemical physical issue with sodic and dispersive soils. In southern New South Wales, the problem is more structural issues with dispersion, and especially for a year like 2016, which was such a wet year, waterlogging affected a lot of those farming systems in sodic soils across the region. In one of our GRDC projects, we are looking at improving wheat yield in these soils, and so we are targeting over hundreds of commercial lines of wheat that are available in farming systems, plus the breeding lines that being developed over the last few years by various breeding programs and also CSIRO. We test these in different environments in South Australia, Victoria, Queensland, Western Australia, and also New South Wales, from glasshouse to the field. So there are different screening techniques, and we breed and we try to assess their performance based on different constraints. And we design, for example, if we are in a hydroponic system, we design a solution that represent a typical sodic acidic soils or acidic alkaline soils, and then we take them from that for further observation in the field to see which variety perform better or perform poorer. And then what we can do is to come back and use at a molecular level, look at those traits to be transferred from a poor crop to a good crop, or vice versa, for releasing a better variety over the next few years, which with tolerance to those conditions. One of the experiments that we have in the last 2 years, it's in Rand near Lockhart in southern New South Wales, and these two graphs are just representing the soil characteristic. It has a fairly acidic topsoil with increasing pH in the subsoil, and ESP, which is the index for your exchangeable sodium percentage and shows how sodic is your soil, increases from anything in 5 to 6% in the topsoil to over 10 to 30% in the subsoil. So in the Australian context, if you have a soil which is more than 6%, it has more than 6% sodium, it's considered to be a sodic soil, but really it's above 10% that you have issues with soil sodicity. As I say, dispersion is important, and the quick test for just seeing if your soil is dispersive or not is called Petri dish test. You put some aggregates in the Petri dish, and if that cloudy pattern of the clay dispersion is observed, you can confirm your soil is dispersive as well. And these Petri dishes are different depths, so the topsoil is not sodic, not dispersive, and the sodicity and dispersion increases by depths from right to from left to the right, as you can see. And so, just a very quick representations of the data that we have. For example, variation in yield in the variety that we choose in 2015. There was about a threefold variations in in yield in response to that site. So the design of these experiments were in such a way that we had 4 replications, and none of the rows had a similar variety on the same plot, so on the same line. So it was a very clever design done by some of our colleagues in Adelaide, in the biometry hubs in University of Adelaide. So there is a massive variations in yield in response to acidic soil in this case, and we looked at many traits from physiological point of view, from nutritional characteristics of plant, and one of the traits that people often use for looking at salinity and sodicity is sodium concentration that is being accumulated in the leaf. And again, in this site, and one of the things that people usually confuse is salinity and sodicity. If you have a saline soil, you have high concentrations of sodium in the system. But in this case, which is a sodic soil, probably is the soil structure that is causing a lot of problem. And sodium is not, as an element, toxic for the plant. So the 4 bars on the right-hand side here are durum wheat, and the rest are bread wheat. And there is not a lot of variation, I have to say, in sodium concentrations in the bread wheat, and that wasn't correlated with the yield either. So that means your yield was independent of the capacity of the capacity of your wheat variety to exclude the sodium from their leaf. In 2016, we had a very similar observation. It was an interesting year because we experienced a severe waterlogging in New South Wales, like anywhere else in Australia, I think. And because waterlogging was one of the stresses that we were really interested, it was a good opportunity to screen these varieties again in 2016. I didn't provide much result for 2016 just because the time wouldn't allow me to go through the details, but there was a massive genotypic variation at 2 levels. The germinations of the seeds in a sodic soil which is waterlogged, and also across the season, some of those varieties that we scored as 0 or 1 at the beginning of the season managed to actually grow later on the spring and catch up with the other varieties that perform better. And it will be used in our future soil and plant interaction work to further investigate what are the traits in those varieties that make them capable of actually coping with that massive waterlogging conditions. When this when you can see this figure here in next slide, so one of the things that we observed that waterlogging in some of the variety caused a massive problem at the time of harvest. As you can see, half of the plot was still green and not really ready for harvest, and the other half, or the other varieties, were quite mature and ready for harvest. So the phenology and the time of flowering and then the maturity was very important when you have genotypic variations between these varieties in a sodic waterlogged condition. One of the traits that we found interesting in both 2015 and 2016 was the calcium to sodium ratio in the leaf, and it was correlating well with grain yield. And again, we tested, or we looked at so many different traits, but one of the very few that correlated with yield was the capacity of that variety to maintain a higher calcium to sodium ratio. So that means the internal calcium to sodium ratio was giving the yield benefits to the crop, and it has a lot of physiological actually interpretation, because in a sodic soil where you have problem with calcium deficiency because of either the sodium competing with calcium for taking it up by the plant, that variety that has a capacity to take up more calcium out-yielded the other varieties. And this is one of the traits that can be used in future for breeding programs if we confirm that pattern in the next few years in different locations. So this final graph from this work is a heat map of a genetic correlation. Okay, so what it shows, it's a very complex graph, but I just try to explain it simply. So what it shows is correlating the variety response in different locations across Australia. And what it shows from 0 to -1 is where the varieties performed opposite to each other, and from 0 to 1 is for the varieties that actually performed similar to each other. And the message from this modeling work was that whatever we do in terms of research and variety assessment in southern region, and that covers New South Wales, Victoria, South Australia, and parts of Western Australia, they are relevant to each other. But those variety or traits that are working in Queensland sites are not correlating well with the rest of the region. So and I think that's the environmental effect and the soil characteristic between the southern region and the northern region that is driving these differences. So it's very important to note whatever we work in terms of research is relevant to the other part of southern region and vice versa. Late in the last season, we also started to use drone technology. Again, I don't want to show any data from this work because it's preliminary first, and second is work in progress. But this season in 2017, intensively we use multi-spectral cameras to look at the changes in canopy temperature, for example, and also NDVI measurements of the canopy using the drone technology that hopefully will give us some high throughput scanning of our trials for relating soil and genetic materials with this technology. So I notice I don't have much time and I have a few slides left, so I'll try to summarize the second part of the talk very short, very briefly. As you remember, I talked about variety improvement and that the best long-term strategy is a dual approach. So the second approach is managing a subsoil constraints with adding some sort of amendment that is capable to tackle that issue. Okay. So we have evidence from high rainfall area that subsoil manuring, for example, have the potential to increase the yield by 50 to 80%. And the photo that I put here is from Peter Sale, who led that work in the last few years. And so GRDC was very interested to look at the potential of this work in medium rainfall area. And and 2017 is the first season that we are going to look at the potential of this work to tackle subsoil sodicity, and we already have another project that is led by Dr. Guandi Lee looking at subsoil acidity. So in 2005, 2006, and 2007, as you can see, we increased, so by subsoil manuring, the yield, the wheat yield of the crops increased significantly, and it has a residual effect over the 5 to 7 years by subsoil manuring. The example that I want to show you here is the work that we are doing on subsoil acidity. So subsoil acidity is important because the high aluminium concentrations in the subsoil, giving the plants, the root, a deformed morphology, which is not capable of going down anymore. So, and most of the subsoil acidity is in that 10 to 30, 35 centimeters. So we really need to target that area to look at the possibility of removing that acidity from that active root zone. So I'm just conscious of time. Luke, would you like me to go ahead, or it has another 4 or 5 slides to go ahead with this.
Sorry, Ehsan, I was muted. I'd personally like you to go through the slides.
Okay, sure.
Yep.
Sure. So in terms of amelioration of subsoil acidity, we conducted recently just a patrol that to look at the potential of what we can do to ameliorate the subsoil acidity. All right. So there are different ways to put our amendments in the subsoil. One is to put in 0 to 10 centimeters. The other way is we could actually target and put it at 10 to 20 centimeters or 20 to 30 centimeters. So in all different configuration, we came with a design of experiment where we could put different amendments at different layers to see what is the potential for removing this subsoil acidity and affecting the performance of that wheat variety. And we use different varieties. So we use different amendments. We use lime as the most common corrective amendments for pH. We also use biochar because there was some evidence that biochar has the potential to increase the pH of acidic soils. We use lucerne pellet, and the reason for lucerne pellet is that it's a very nitrogen-rich amendment with the capacity to also affect the pH. And we use magnesium silicate as another amendment. And magnesium silicate, at the presence of water, produce magnesium carbonate, and the magnesium carbonate is alkaline. So, and there are a massive deposit of this in New South Wales. So we just looked at this amendment as an innovative material that could be used in future. Okay. At the end of experiments, we looked at soils at different layers, and we looked at the root morphology and looked at the plant traits, and I will just explain very quickly snapshots of the result that we obtained. Okay, so these graphs here, it's a bit busy, so I'll try my best to explain them on a simplest way. The bars showing you the dry weight response, the percentage of the control, okay? So whatever the control was, this is relative to the control treatment. And you have biochar, lime plus lucerne pellet on its own, magnesium silicate, or magnesium silicate plus lucerne pellet. So the idea of having an inorganic amendment plus lucerne pellet is to see if we get additive effect. And the circles here, the black dots, are the changes in pH. And the control pH is that red square. So the effect of the pH, which is the scale is on the right-hand side, is represented by those circles. So in a very quick glance, what we can see, yeah, we get about 5 to almost 8% increase in your dry weight relative to control when you put your treatment at 0 to 10 centimeter. Magnesium silicate plus lucerne pellet was a surprise. It gives us 25, and we still are working out why we get that response. But when we are tapping into that acidic subsoil layer at 10 to 30 centimeter, the increases are becoming more evident. So we are the dry weight relative to control is actually increasing by 20 to 30%, and in some of those treatments is similar at 0 to 30%. But it's as what I liked, you note that important layer was 10 to 30 centimeter, which was the most acidic layer. And I did a coefficient of correlation. So that is correlating the changes in your plant response to your treatment layer. And that correlation becoming mostly significant from like 0.39 to 0.84 when you're starting to put your amendments instead of in the topsoil, in the subsoil where the problem is. And one of the reasons to explain this, that why is this happening, is related to the exchangeable aluminium. In this graph, on the x-axis, you see the changes in pH, and in the y-axis, you see the exchangeable aluminium in the pot. In your 0 to 10 treatment, you are just removing about 10% of that exchangeable aluminium that is in your soil. However, if you are targeting your subsoil acidity, you are removing up to 30% of that exchangeable aluminium, which is toxic for your root. However, if you just focus on the topsoil, 0 to 10, when you're adding your lime in the farm, you are ignoring that 30% of toxic aluminium in the subsoil. So really important to notice how crucial it is to remove that exchangeable aluminium by this either liming practice or adding organic amendments in the subsoil. And that brings us to the machinery of this work, what we can do in terms of having these amendments. There are different versions of subsoil deep ripping available. I think the best and the most capable one is the one that is designed and built in New South Wales DPI at the moment. And that is done by one of our Genie and technical officer, Adam Larry. But in the past, quite a few of these being built. And so it is feasible, and we are just, but definitely it needs to be more cost effective, and the material that you put in the subsoil needs to be designed and manufactured according to the problem. We are also getting some newer technology coming to Australia, pelletizing biomass on farm and off season. So you can grow your own stubble. You can have your own stubble, and with these pelletizing machines, you can produce your own pellets that can be incorporated into the subsoil and getting that organic submanuring sorted. So I want to leave you with, again, with this photo, two examples of amelioration of subsoil acidity on the left-hand side. This is a site in Ferndale in southern New South Wales. And then the photo on the right is the ameliorations of subsoil sodicity in high rainfall area of Victoria. And as I said, this is just research that we recently started, and hopefully some good results will be obtained over the next 3 to 4 years. In summary, what I wanted to highlight is that wheat varieties are definitely different in their tolerance to various soil constraints, and there is a hope that we can use various traits that are driving this tolerance of wheat varieties to multiple stress conditions for producing better varieties. And the sites that we've worked in southern and western regions are strongly correlated with each other, but there were different differences with the Queensland signs. And then on the manipulation, on the subsoil constraint part of the story, the benefits of having tolerance to multiple stresses. Actually, this is for the first part. So what we found in our initial analysis is that the benefits of having tolerance to multiple stress is for those sites that has yields below 3 tons per hectare. Okay. And when you are doing your subsoil constraint work, there are some factors that are really important to notice. Season is important, how much rainfall we get. The location is important, soil type, and the level of constraints. It's most likely that you get the benefits from subsoil work if the constraints is really severe, and if it's just mild or not really severe, the potential to get economically feasible benefits from this work is less. And at the end, I just wanted to acknowledge the work again that is being carried out by different people in Wagga Wagga Institute and our collaborations at University of Adelaide and UniSA. Thanks.
Thanks, Ehsan. Fascinating talk. I've got about 1,000 questions of my own, but we've got a couple of people there. What I might start off with doing, Ehsan, is could you briefly explain the handouts that you've got there for people and what's in them?
Sure. So the handouts are related to subsoil acidity project, and that project is led by Dr. Guandi Lee. And The fact sheets that we produce from the result from the first 2 years of experiment is the result of one of our experiments in Holbrook, and the other one is related to that subsoil deep ripping machine. And I thought people might be interested to look at more information about that deep ripping technology that we designed and built in Vaga, and also some of the early result of what we did in field to tackle subsoil acidity. So both of them are designed by New South Wales EPI and available online on the website as well.
Thanks, Ehsan. Okay, so we'll take questions. Mickey Wang.
I just want to ask, for the, not related to the soil, but related to the project you're doing now, you use the infrared camera on the drone to scan the crop. Did you only just compare the temperature difference between different treatments, or you doing something else?
Okay, so we haven't done the canopy temperature yet, but what we did so far is just to look at the leaf green index, which is the NDVI. But
okay, yeah.
What we want to do in the future is, yes, we can look at the either different varieties. For example, if you have 40 or 50 varieties, and if there is a difference in canopy temperature between these varieties, that may means that you have a different transpiration, which means it's a different water use by the plants. Yeah. And the plant that have, for example, a better water use, they are always having a cooler temperature because of the higher transpiration. Alternatively, yes, you can look at different treatments, for example, and the treatment that give you more water access again means that your plant taking or transpiring more water, and that will be reflecting in canopy temperature. So it's just not about temperature, but also about, as I said, NDVI, and also we picking up necrosis and chlorosis on the canopy that may indicate some nutritional disorder that is providing a very quick and fast scanning tool to look at the whole experiment.
Okay, well, that's very good.
So the next question, we've got a hand raised from Levinus Emabiri.
Your results seem to suggest, in fact, that we have two issues here. We have subsoil constraint due to chemicals, and also the soil structure. My question then is, do you have information on what kind of root threads that can be more useful in breaking up the soil structure?
The important thing is to notice is that the root on its own, when we do, for example, selection for a better variety, the root on its own should have, in that better variety, should have the capacity to penetrate further. So that means if you have a hard pan, that root must be capable to go through that hard pan and access the water which is stored in the subsoil, compared to a plant or a variety that doesn't have that capacity. So it's not about just one root trait to for example, mention, but there are some work that looked at, for example, on root hairs and the higher specific root volume that is capable to have access to the water and nutrients in the soil. But just focusing on breeding in conventional way for those varieties that perform better, that performance is related to the capacity of the root to penetrate into the deeper soil. And then if you're talking about the primer crop, like lupin, which can, for example, go down and make some cracks into that soil structure, that's a different topic. That is just using that plant, for example, or that technique to open up the soil structural issues for your next crop that you put, for example, after that. I don't know if I answered that question properly or not,
yes.
But
thank you very much. That's good.
Okay, thanks, Lavernas. So Mark Arundel is the next person with a question.
Oh, the question is, you mentioned something about gypsum as a potential amendment for sodic soils. One of the things I've been working with lately is exfoliated vermiculite, and one of the issues we've found is there doesn't seem to be much research in the use of vermiculite in subsoil conditions. I would have thought in something like, hostile soils, the potential of vermiculite would be quite strong. Are you aware of any work that's actually been done with it?
So you are right. There is not a lot of research being done, and whatever is being done, to the best of my knowledge, it doesn't really explain why the changes being observed in, that soil physics or chemical structure. Quite a bit of work is being done in WA, in sandy soils, where they added vermiculite into their soil. But one of the aims of this project is to use innovative material that have the potential to be used for treating the hostile soils. So I'm always open to, test this material at the glasshouse and the field level. One of the questions always is about the feasibility and the cost of this material, that how much do you need, and if it is economically feasible to be applied at the field level. But I'm not heavily up to date with the latest research on that. But there were a couple of releases on GRDC website on that, I think 2 years ago.
Great, thanks, Mark. We've got quite a few more here. Janelle Jenkins, who's down in southern New South Wales as well, and with a wealth of experience, has made a comment here which I think is really worth making.
Yeah, so my comment basically was that we've been doing some soil sampling down here in the Riverina, in the moderate and the high rainfall areas, mixed farming areas. And of all the samples I've taken where I have a subsoil and a topsoil sample, 2/3 of them are showing subsoil acidity problems. So basically the problem is huge and growing. So that was all my comment was. So the sooner you can get a commercial machine that will actually take care of the problem, the better.
Sure, and it will be to be in touch with you in future to make sure we cover that area for our trials if you have anything to go in 2018 or 2019.
Well, I've got a heap of sites that you could potentially use because I've got the data on the 0, the 10 to 20. Yeah.
Absolutely.
Yeah, look, just probably final one from me, Ehsan. Just you didn't touch on perhaps the economics with putting in the subsoil organic matter. Do you have any comments just on the economics of that for farmers, please?
Sure. So both of the project, the subsoil acidity project and the subsoil sodicity project that we are working, they have an economic analysis component. So by the end of the project, we put all these data to a farm economist, and their job is to come with an answer if this is feasible or not. And actually, we are doing it as we go. But the reality is that, and I talked to a lot of farmers in this southern New South Wales region, that this work, the subsoil manuring and subsoil amendment, has a very high upfront cost. And the hope is that the practice will leave the farmer with about 7 to 10 years of residual effect. So you are doing this in year 1 and you still get benefits in terms of yield, yield potential over the next 5, 7, 10 years. And if that's the case, and that's our philosophy to work to practice the best way that we can to increase that residual effect, definitely our first analysis or initial analysis shows it is you pay off the cost within the first or second year, and then then that's definitely economically feasible.
Great. Thanks, Ehsan. And a final comment from you, please. Obviously, this is ongoing work. How do people keep in touch with the results? Is it GRDC web updates? What's your plans for as you get your results, getting them across to advisors and farmers?
Sure. So every year we are presenting the data at GRDC update in Wagga. That's definitely happening. And then over over the life of the project, we have fact sheets that we have to develop through the DPI New South Wales and also our collaborators with the grower groups. So they've, as the project progress, all this information will be fed into farming community in every possible way that we can plan for that. But definitely there are 2 or 3 ways of communication. As I say, GRDC update and grower groups are our 2 main pathways for communication.
Sorry, did you mention any particular grower groups, or are you open for all grower groups? Or
so the subsoil acidity project is working with Holbrook and FarmLink Research. Okay, so they are involved in the project, and for subsoil sodicity, I'm negotiating with the relevant grower groups to be involved in the project in order to communicate the result. So it's just the first year of that project, so we have still a bit of time for studying up the pathways. But GRDC update in 2018 will be the first year to communicate the data from subsoil sodicity project.
Oh, fantastic! We look forward very much to that, Ehsan. There's a lot of interest in us. Janelle pointed out the size of the problem; it's just massive. So fantastic work and really interesting. Oh, we've got Jeff Mentions put in a late comment. Go ahead, Jeff.
No worries. Just a late comment is that we've got a significant body of work of pH mapping and EM survey work that was done over the last 12 months. So just a comment on the economics, that if you are just treating the hardest affected zones in a paddock, the economics will stack up a lot better. So be keen to talk to Ehsan about the work we've got with that type of work, PAs type work, and the soil testing that's going on there. And it might be useful to have a look at some sites to do some economics as a desktop exercise more than anything.
I would be very interested, Jeff, absolutely. And as you see in that summary page at the end, I say it really depends on the level of the constraints. If you have a severe problem and you target that area, that's the highest chance to get your economics right. And I would be very happy, to have a desktop exercise with you and your data whenever possible to look at the feasibility in terms of the economics.
Sounds great.
That's great. All right, fantastic talk, and obviously huge amount of interest in the topic. Thank you so much for a very informative webinar, and we look forward to having everybody back for our next webinar coming up in about a month's time, usually the first Thursday of the month. So I'll call that quits. Thanks, everybody.